Okay, so this problem reads, a 50.0 gram sample of calcium carbonate reacts with 13 grams of hydrochloric acid. How many grams of calcium chloride are produced? All right, and it gives you the reaction. Okay, so it says, calcium carbonate solid. Luckily, we haven't done acid naming yet, so hydrochloric acid is HCl. And then you get calcium chloride, carbon dioxide, and H2. Do you notice something different about this problem from the previous? How many grams is it giving you now? It's giving you, it's giving you 2. It's giving you 2 grams, two different quantities instead of just 1. So you don't have to do an amounts table for every problem. You just have to do these when it's a limiting reactant situation. All right, so I can tell it's limiting reactant when I have 2 different grams of reactants. So I'm given 50.0 grams of calcium carbonate, 13.0 grams of hydrochloric acid. And now it's asking me how many grams of calcium chloride are produced. All right, let me write the chemistry up here. So I've got calcium chloride, 2HCl, and okay, so the first step after you balance, what does it tell you to do there? It says produce an amounts table, putting the initial moles in for the initial amount. So initial change, final. That's what ICF stands for. Initial change and final. So let's calculate the moles of calcium carbonate that we have here. So 50.0 grams calcium carbonate. How do I get to moles of calcium carbonate? Right, so grams of calcium carbonate, molar mass of calcium carbonate is 100.09. And that comes out to be 0.5. All right, we're going to take that 0.500. And by the way, I'm carrying at least 3 sig figs here because I got 50.0. I'm going to make my spreadsheet here. So I got 0.500 moles of calcium carbonate. I'm going to do the same thing for HCl. .0 grams HCl. Molar mass of HCl turns out to be 36.46 grams of HCl for every 1 mole, and I end up getting 0.357 moles. So I've calculated the grams into moles for each one of my reactants. What numbers do I put for these guys, for the initial? Reaction hasn't started yet, so they're always going to be 0.
Why 0 moles?
So they're all 0 because the reaction hasn't started yet. This is the initial quantities that we have.
Oh, okay.
So those are all 0. Okay, so if I look at this now, how do I know which one of these two runs out? How do I know which one of these two is limiting?
The smaller one?
So I can look at the smaller one and say, all right, it's less than this. It's not quite that simple. What you have to do is you have to divide the initial moles. In this case, 0.357, you have to divide it by 2. And for calcium carbonate, it's 0.500 divided by 1. And whichever result comes out the smallest is your limiting reactant. Now, it might seem easy to see it now, because this is 0.357 is already lower than 0.5. And dividing it by 2 is just going to make it even smaller. So clearly, HCl is a limiting reactant here. But sometimes, okay, what if the coefficient for calcium carbonate, it ended up being, say, like 4? Okay, then this would come out smaller. Okay, even though there's more moles initially starting out with. So the stoichiometry matters. Okay. Okay, so dividing each by their own coefficient. So this divided by 1, this divided by 2. I get 0.178 for the HCl. I get 0.500 for the calcium carbonate. This one is smaller, so it's my limiting reactant.
HCl.
Yeah, the HCl is going to be my limiting reactant. I want to make this really, really clear. These numbers that you get, you don't do anything with them. You just use them to make a decision as to which one ends up going to 0 for the final amount. But I do not put these numbers into the table. I keep putting my initial moles into the table. All right, really, really important. So now that we know HCl is limiting, this allows me to do this. I know this is limiting. It runs out. So I'm going to subtract out all of my HCl moles from the initial, and I know I'm going to have 0 left. And here's something else I can do. Because the limiting reactant limits how much product I can make, it also limits how much other reactant I lose. So I'm going to take that 0.357 and put it in all the other columns. Notice I'm using blue because it's all based on my initial moles of HCl. So the reason why this amounts table, you're going to find it in the long run to be so much better than whatever the textbook tells you right now, is because sometimes the question may ask you how much of each product is produced, how much of any reactant is left over. Right? It may ask you for multiple answers, okay? Especially when you get to Chem 111A, you'll get questions like that. And if you don't know how to do the amounts table, it becomes a lot more difficult. Okay. Now that we have our limiting reactant, now we have to establish the stoichiometry. We got to stoic it out. Okay, so if I relate the moles of, HCl that I lost to the amount of product produced, notice how I have plus signs for all of my products, but for all of my reactants, I've got minus signs. Again, we're losing reactants, but we're gaining products. So that's why we have the sign change. My stoichiometric ratio, I'm going to put in each of the change column, or excuse me, change row. I'm going to put my stoichiometric ratio for each box in there. So if I look at the stoichiometric ratio of calcium chloride to my limiting reactant, which is HCl, it's going to be 1/2. I've got 1 mole of calcium chloride produced for every 2 moles of HCl that I consume. So moles of HCl get reacted away or canceled, and I get moles of HCl here. So I end up forming 0.178 moles of calcium chloride. Okay, so what I'm looking at here is, let me pick a slightly different color here. I have a coefficient of 1 for calcium chloride, and that 1 goes right here. All right, and then this 2, so that was a 2, and this is going to be a 2 here. So check this out. I'm going to use that 2 as a denominator in all of my other columns. So this bottom number, what do you think it's going to be? 2. Bottom number here, it's going to be 2. Do we need a ratio here? We don't, because this one's limiting, so we don't worry about that. That one's running out. Bottom ratio here, again, 2. Okay. This 2 goes in the denominator of all of these fractions for all the boxes.
So if it was CaCO3, that was the one limiting, then you would put 1 in the denominator?
Yep.
Oh.
Yep.
I'm right.
So just in case you didn't hear it, Orpha asked, well, what if calcium carbonate was limiting? Well, this has a coefficient of 1, so if calcium carbonate was limiting, then the 1 would go here instead of the 2. What goes in the numerator then is the coefficient for that column. So this is 1 for calcium carbonate, so we put a 1 here. This is a 1 for calcium chloride, so that's, again, a 1. In fact, all of these are 1. But that's not always the case. A lot of the time, different products have different coefficients. All right. For the rest of the products here, 0.357 times a half gives me the same number as what I got here. So I'm just going to write that in here. I'm going to fill in this table. All right, last box we got to fill in is the final amount of our excess reactant. What goes here is we say, okay, let's go ahead and subtract this entire quantity from the initial. So if we say 0.500 minus 0.357 times a half, we would get some answer here. All right, so let me write out what we would get. So this is what you want to punch in your calculator. It's 0.500 minus, and in parentheses, 0.357 times a half. Right, so you want to say 0.357 times a half and subtract that entire amount from 0.500. If you if you type in 0.500 minus 0.357 and then times by half, you'll get a wrong answer. All right, so really important to understand, you're taking the entire quantity calculated out in the change box and subtracting the result from 0.500. Okay. So the end result here would be something like
0.321.
and 0.322.
322.
And 0.322.
Yeah.
I'm going to say moles of calcium carbonate left over, right? That's the excess reactant, that's what's left. And then these are all products that were produced. All right, so let's get to the actual question of the answer that it asks us. Okay, it says, it happens real fast, you'll see. How many grams of calcium chloride are produced? So how many grams of calcium chloride are produced? This should be really easy now, right? We got moles produced. How do we get to grams produced?
We gotta convert.
Multiply by molar mass, right? So getting to the home stretch here. Mass of calcium chloride mass of calcium chloride produced equals 0.178 moles of calcium chloride times the molar mass of calcium chloride, which comes out to be 110.98 grams of calcium chloride for every 1 mole of calcium chloride. Okay, and that would come out to be, with sig figs and all, 19.8 grams of calcium chloride. This looks like a lot of work for one answer, but we didn't get just one answer. All right, go to the next slide. Okay. The next slide asks you how many grams of calcium carbonate are in excess. Okay. Mass of calcium carbonate in excess that's equal to 0.322. Moles of calcium carbonate divided by the 100.09 grams for every 1 mole of calcium carbonate. So this 100.09 is the molar mass of calcium carbonate, right? This is the molar mass of calcium chloride. Oops, oh wait, sorry. Just say, nah bro, right? That's not right. My bad. Multiply by the molar mass. Okay, so times 1 over 1 mole of calcium carbonate. Okay. And that gives us 32.2 grams of calcium carbonate left over. And I could easily do a similar calculation for CO2 and water if I wanted, right? If I wanted to do it. So I know I just showed you a big, like, brain full of numbers. But if you get used to doing it like this and continue doing it in 111A, you'll be better prepared for 111B when you get there. Okay. You can see why I wanted to video record this, right? You're gonna need to watch this over and over again. All right. But what do you think? Pretty cool?
Yeah, I like it. That's good one.